You're staring at a curve. Smooth, elegant, suspiciously innocent. Someone shades the region underneath it between 2 points, A and B, and asks, how much area is that? And just like that, your peaceful afternoon is over, because that shape is not a rectangle, not a triangle, not anything your geometry teacher prepared you for. It curves, it bends, it refuses to be simple, and yet we still demand a number. So what do? We approximate. We slice the interval from A to B into small pieces. Each piece has width delta x. That just means a small change in x, but really it means we're about to get sneaky. Over each tiny interval, we draw a rectangle. The height of that rectangle is given by the function value, f of x. So each rectangle has area f of x times delta x. Now we add them up, all of them. That sum is called a Riemann sum. It is the process of approximating the area under a curve by adding up rectangular pieces. Not perfect, not exact, just an approximation. But we're not satisfied with pretty good, so we make the rectangles thinner, and thinner, and thinner. We let delta x shrink towards 0. Not become 0, just approach it. And when we take the limit of that Riemann sum as delta x approaches 0, the approximation becomes exact. That limit has a name. It is called the definite integral. The definite integral gives a number. That number represents the exact accumulated area under the curve between A and B. That stretched out S is not decorative. It stands for sum, a sum of infinitely many infinitely small contributions. The definite integral gives a number. That number represents the exact accumulated area under the curve between A and B. Now let's raise the stakes. Suppose the function represents velocity instead of just a random curve. You plot velocity versus time. What does the area under that curve represent? Velocity times time equals distance. Each tiny rectangle represents a tiny distance traveled during a tiny time interval. Add them all up and you get total distance traveled. This is the deeper meaning of integration, accumulation. The definite integral accumulates tiny changes into a total quantity. Area is just one interpretation. Distance is another. Mass, charge, energy, probability. All of them are accumulated through integration. Now we shift gears. So far, the integral had limits. It gave us a number. But what if we remove the limits? Now we have what is called the indefinite integral. The indefinite integral does something different. Instead of giving you a number, it gives you a function. Specifically, it gives you a function whose derivative is the original function. Integration, in this sense, is the inverse operation of differentiation. If the derivative of x squared is 2x, then the integral of 2x is x squared plus c. That plus c is not optional. It is called the constant of integration. When you differentiate a function, constants disappear. So when you integrate, you must include all possible constants that could have been there originally. The indefinite integral produces a family of functions, not just one, a whole family separated by constants. Now, here's where everything connects. The definite integral and the indefinite integral look like different ideas. One gives numbers, the other gives functions. But they are connected by one of the most important results in calculus, the fundamental theorem of calculus. It states that if capital F is an antiderivative of little f, then the definite integral from a to b of f of x is equal to f of b minus f of a. The infinite limiting process of adding infinitely many infinitely small rectangles can be computed by finding an antiderivative and evaluating it at the endpoints. This theorem connects accumulation and antiderivatives. It tells us that integration and differentiation are inverse processes. The definite integral measures total accumulation, and the indefinite integral provides the tool to compute it. Now, reality check. Not every function is cooperative. Sometimes you encounter something like the integral of e to the x squared. You search for an elementary antiderivative. It does not exist. There is no simple algebraic expression for it. When that happens, we use numerical methods or define new special functions. But the concept of integration remains the same: accumulation through limiting sums. Now let's talk about something slightly unsettling. When we compute an integral, we are summing infinitely many quantities that are individually approaching 0. Each delta x becomes extremely small. Each rectangle becomes microscopic. And yet, the total area is finite. How can infinitely many nearly zero quantities produce something meaningful? Because in calculus, approaching 0 is not the same as being 0. Limits allow infinite processes to produce finite results in a controlled way. That control is the foundation of integration. So the next time you see the integral symbol, don't see a monster, see a machine. A machine that turns rates into totals, density into mass, velocity into distance, tiny pieces into something whole. You started with a curve and a question. Now you understand the mechanism behind the answer. And if your brain feels slightly stretched right now, good. That means you just wrestled infinity and survived. Thanks for watching. If this helped you see integrals differently, consider subscribing, leaving a like, or dropping a comment with the next topic you want to conquer.